Hey, grade 11. Someone asked me about trying to calculate the amount of energy given out and calculating the mass required to give out that amount of energy. Now, there's two ways to do this. I don't think that there's one way that's particularly quick or preferred, and it might just be down to what you prefer to do. So I've wrote down this question here. If one instance of fission releases 200 mega electron volts of energy, then how many grams of uranium-235 is required to produce 4 gigajoules? So I want to go through this first on the left without using Avogadro's constant, and then again on the right, slightly different method using Avogadro's constant. So let's get started then. The first problem here is that we are not in the same units. So we're going to try and normalize that. Now 200 mega electron volts is equal to 2 times 10 to the 8 electron volts. And 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Okay, so all we're going to do is multiply these two values together, and we're going to calculate the amount of energy in joules. What we find then is that that's 3.2 times 10 to the 11 joules. Now then, we know how many joules of energy we want, and that's going to be 4 gigajoules. So giga times 10 to the 9. So we've got 4 times 10 to the 9 joules that we want, and every single individual interaction, every time uranium undergoes fission, we get 3.2 times 10 to the minus 11 joules. If we complete this calculation here, then we know exactly how many times we need to undergo nuclear fission. So that's going to be 1.25 times 10 to 20 occasions. Okay, then the next thing that we're going to do is we're going to try and approximate the mass of uranium. Now, you might be given a value for the mass. If that's the case, definitely use that. If you've got to approximate it, then, well, what we're going to do is we're going to say we've got 235 nuclides in the nucleus. We're going to multiply that by the unified atomic mass number, which is in your data booklets. In kilograms, that mass, and that's the value we want, right? We want it in kilograms at the end. So that's going to be 1.661 times 10 to the minus 27. If we do this calculation, then we find that one individual uranium atom should weigh roughly 3.9 times 10 to the minus 25 kilograms. And now all we've got to do is we've got to multiply these two values together. So we know how many reactions we need, and that's just up here. And we know how much one interaction weighs. So we're going to multiply these to 3.2 times 10 to the 11 multiplied by 3.9 times 10 to the minus 25 gives us, in kilograms, for give or take 4.8 kg. Okay, so we're looking at about 4.8 kilograms of uranium, way less than 1 mole. And remember, 1 mole of uranium is 235 grams. Oh, sorry, that is a little mistake. Not 4.8. 4.8 times 10 to the minus 5. Only about 100,000 times out there. Sorry. Yeah, that's the mass that we're going to have there. Okay, so let's look at doing this another way then. We're going to use Avogadro's constant this time. And we're going to start by taking a look. Well, if we have 1 mole, 235 grams of uranium, 235, how much energy is that going to give us, right? And this is going to be quite a quick way to get a value for energy. So we're going to say 200 mega electron volts is 1 instance of the reaction. So 2 times 10 to the 8 electron volts. And we're going to multiply that by Avogadro's constant, which is 6.02 times 10 to the 23. All right, and what we've got now is, this is going to give us a value, an amount of energy if we have 1 mole of uranium. That comes out to an absolutely ginormous, pardon me, that comes out to 1.2. Why is that doing that? Hey, sorry about that, I had a technical problem. So we can find that if we multiply this out, then we're going to get from 1 mole or 235 grams of uranium, we're going to get 1.2 times 10 to the 32 electron volts. Similar thing, we're going to convert that into joules because that still needs to be done. If we do that, we find that it's 1.92 to the 13 joules. Now obviously that's a lot more than 4 gigajoules, right? So it's going to be a fraction of a mole that we need. And let's find out how much exactly that is. So if I take the amount that we actually need, just 4 gigajoules, 4 times 10 to the 9 joules, divide that by the amount of energy we get from 1 mole, 1.92 times 10 to the 13. Then we find that we actually need 2.076 times 10 to the minus 4 moles. 1 mole weighs 235. So 235 grams multiplied by 2.076 times 10 to the minus 4. And that's going to give us the value in grams. So that's 0.0487 grams. So obviously that tiny fraction, like a few thousandths of a mole, a few thousandths of 235 grams gives us 0.0487 grams. And if we take a look at that and turn it into kilograms, so we can multiply this by, divide this by 1,000, then what we end up with in kilograms is 4.87 times 10 to the minus 5 kilograms. And then that's worked out perfectly. Right, so we've got basically the same value. There might be a rounding error, I'm not sure about this 4.8 here, but the same value, but 2 different ways of kind of going about that method there. Hopefully that was helpful. Thanks for asking the question. Bye bye.